So hey everyone, my name is Ganesh. I'm a lead engineer at Replica. So far, I've been working at various aspects in the company, but most recently, I've been taking charge of the development of our TypeDB cluster, which is the other flagship product sitting side by side with TypeDB. Before going into talking about TypeDB cluster, let's take a look at what TypeDB has for us as a product. So TypeDB, as we all know and love, is a product intended to solve data complexity, right? And what that means is that it allows you to build an application leveraging its schema language to basically model complex data. In addition to that, you're also able to then query this data in a meaningful way, all enabled by the expressive, powerful, but also strict query language, which we call the TypeQL. So the notion of packaging a strongly typed modeling language in a database is basically the main value proposition of Graphing, which enables us as an application developer to build an application concentrating on the business logic rather than the technicalities of building a working database system, right? Allows you to basically express your business logic in a way that is strict and also not ambiguous. So all of this results in increased productivity because the less errors you make, the more productive you are. So now that if you're building your application, you're happy, you have your application ready. So what's the next step, right? Well, the next step is for you to be able to take this application and run it in production, serving real people, right? So for a system to sit in production, running and being used by real people, there are additional challenges that you're facing. So not only you have to build an application that that leverage an expressive type system, which TypeDB provides, we also need the system to be, first of all, secure. It needs to be scalable, being able to adapt to changes in user demands, right? The system will also need to additionally be quite available. You don't like system that goes down every, every once a day, right? So we want the system to have minimal downtime. And that is the main value proposition of TypeDB Cluster. TypeDB Cluster is intended to tackle not just complexity, but also does so at scale. TypeDB Cluster is scalable, meaning that you can run your application against a cluster of TypeDB Cluster instances, making sure that you can grow the size of the cluster based on the user demands, right? Like, say you're building an e-commerce application and tomorrow is Black Friday and you need to be able to handle more loads than usual, then what you can do is you can increase the size of the cluster, right? In addition to being scalable, TypeDB Cluster is also highly available. What that means is that should some of the instances go down, it is possible for the cluster to still be fully functional. And this allows you to minimize downtime, because what that means is not only it allows you to be tolerant to server crashes or network outages, you're also able to maintain the system in a continuous way. Think upgrading the operating systems. Think increasing the disk size. All of these operations sometimes require you to restart the server, shut down the server for a bit, for like 5 to 10 minutes or even more. And you can do so while being sure that there are other database instances that are still live and serves the customer. You can perform these rolling updates, making sure that systems are gradually upgraded, but also at the same time maintains the uptime of the system. TypeDB Cluster is already running in production. It's being used by, for example, ourselves. We are on dog food So we have our CI system, which is called Gravel.io. I'm pretty sure some of you have heard of it. But basically, Gravel.io, which will be called Particle Factory in the next iteration, right, is the CI system, the primary CI system that we use for us to test and build and release our code base. So Factory or Gravel is running on a TypeDB cluster of size 3. It has a cluster it has a 3-node cluster, basically. So let's take a look at this diagram and simplify it a little bit because I want to make room for us to take a look at what's inside TypeDB cluster. So let's take a look at this diagram in which we have a typical deployment of an application that you have and a cluster, and the application will be connecting against the cluster. The cluster is the like the 3 green big boxes inside the cluster with the green border, right? Those are the servers, and in this deployment, you have 3 servers. The application needs to connect to the cluster of size 3, right? And say that the application needs to work with 2 databases in this case. Let's call it DB1 and DB2. So the cluster has 3 servers, right? That's the first concept that we need to be aware of, that the cluster is composed of some number of servers, which in this case is 3. And additionally, the databases in TypeDB cluster has multiple copies. Each server contains exactly 1 copy of the database, and we refer to these copies as replicas. So in this case, you'll see that in the diagram, we have 3 replicas of DB1, each of which is sitting on server 1, server 2, and server 3. So I'm just going to call the servers server 1, server 2, and server 3, starting from the left to the right, right? So we have these 3 copies of DB1. And similarly for DB2, we also have 3 copies. Right. So these copies, or these replicas, are essentially an identical copy of one another. So the replica in server 3 will be the same and has the same, by the same, I mean, has the exact same identical data as what's in server 1 and server 2. However, different replicas may play different roles during the lifetime of the system. So in a cluster, you will have 1 replica to be designated as the primary replica. And the rest of the replica will be designated as the secondary. And this is true for every databases that you have in TypeDB cluster. So in this case, you can see that the primary replica of DB1 is sitting on server 1 on the left, whereas the primary replica of DB2 is sitting on server 3 on the right. So why does this matter? Like, what's the difference between primary and secondary replica? Well, the primary replica is basically kind of like the boss replica, and it allows, well, it's the one responsible for handling typical read and write requests from the application. So say in this diagram, right, we have the application that wants to talk to DB1 to perform some, data insertion or some match query. And what it's going to do is the application will talk to the server number 1, in order to connect to the primary replica of DB1. Now, in this instance, say that the application also needs to talk to DB2 to perform other kinds of operations for the data that is stored in DB2. And what's going to happen is the client, sorry, not the client, the application will connect to the primary replica of DB2 sitting on server 3. And as you can see here, the application can make simultaneous connections to different servers depending on the operation and the given database that it needs to operate against, right? So being able to split the replicas per databases is a design decision that we can take and that we took that allows application to scale to some extent, because there is a form of load balancing that is going on here, such that the operations for DB1 and operations for DB2 are sent to different servers instead of all of them are sent to the same server. So this design is a different design than some other database systems. In some other database systems, typically you designate one server to act as the primary replica for all databases. So on those kinds of systems, the operations that goes to DB1 and DB2 will be received by the same server. And the drawback of that is that there is less work distribution that is going on between different databases. Whereas in our case, the split has allowed us to enjoy more even workload across the cluster. Now let's say that at some point, one of the server goes down. So in this case, let's take this example, right? The first server crashes for some reason, maybe it runs out of memory or some other reasons, right? So what's going to happen in that case? Well, what's going to happen is that the application performing operation to DB1 will be transparently switch from connecting to server 1 to connecting to the next server that hosts the primary replica for DB1. So there's something interesting going on here, which is the replicas, they're communicating with one another. And at some point, the remaining replicas will realize that the primary replica of DB1 is, for some reason, unavailable. So at that point, the remaining replica will start to discuss amongst themselves to designate one of the remaining replicas to become the primary. So let's say in this example, the second server, server 2, is now designated as the primary. Once this is done and decided, the application will eventually receive the information that the primary replica of DB1 has been transitioned from the now unavailable server, server 1, to server 2, and the application will be able to transition to connect to server 2 quite seamlessly. So we've talked about how to perform a regular read and write operation, and we've learned that there are some load balancing going on to some extent, such that operation that goes to different databases may be performed to different servers, right? But it may be possible that you still want to achieve more performance. You want the load balancing to not only happen between different databases, but also in the same database. Let's say you're performing a very expensive analytics or reasoning queries, which is done against database 1, right? Reasoning queries can be quite compute intensive, right? And if you perform multiple queries, multiple expensive queries to the same server, you start to wonder, is there any way to leverage the fact that there are other idle servers running, despite the fact that the queries that you want to perform is done against the same database? Well, the answer is we've introduced an additional mode for doing reading of data in TypeDB Cluster, which we call the read any replica. So in read any replica, the application is able to perform, like fire queries one after another, and for each query to hit different servers evenly. So if, say, you perform like 6 queries in this example, it is possible in this mode for the application to fire the first request to server 1, second request to server 2, and third request to server 3, and so on and so forth, essentially allowing you to achieve maximum scalability. If you need to handle n times more requests, then in theory, what you need to do is you just need to add n more servers. So this mode allows you to scale much better, right? However, this reading mode has a drawback in which the operation that you do to secondary replicas instead of primary replicas may not see the latest data. So this is a trade-off that you must take, and TypeDB Cluster allow you to make the trade-off in a way that you see fit. So if you're performing a query that modifies or reads the latest balance of a user account, then most probably you want to use the regular read and write that goes to the primary replica, because that way the operation that you do will never see an outdated data, and is always performed against the most recent form of the data. Because this user bank account, user balance is sensitive, right? You obviously want the data to stay consistent. However, there are other kinds of scenarios where, for example, you want to perform some expensive reasoning queries to basically aggregate the data of how many people are, doing a transaction on a given day, in a time frame of say 5 years, like in between like 2016 to 2021, how many transactions do people roughly do on any given day, right? So these kinds of query are expensive, but at the same time, they can tolerate some staleness in the data. It's probably fine for you to miss the data that has been added like 3 minutes ago, or even like 2 seconds ago, because the latency won't be like 3 minutes. It's going to be like in a matter of like milliseconds or seconds, right? It's probably okay for you to not see the latest data that has just been inserted like half a second ago. And in this case, you definitely want to go with the read and replica option. Now that we've talked about the high-level conceptual model of TypeDB Cluster, the fact that we have multiple replicas for database, and the fact that we expose different kinds of reading mode and writing mode for operating against the replicas, right? Let's go dive a little bit deeper into the internals. Specifically, right now, let's try to take a look at understanding on how does a client know to talk to which server. So we call this step the client mediation step. I'm making the diagram a little bit bigger here. We have the application, and we still have the same cluster as before, a 3-node cluster with DB1 and DB2, right? But we're zooming into the application bit right here, in which the application contains the TypeDB client. As you know that for your application to connect to TypeDB or TypeDB cluster, you'll need to use the client driver, the TypeDB client, which is available in Java, Python, and Node, right? And there are upcoming clients coming from the community, such as the Julia client and Haskell client, and the C# client as well. So in this language, you'll be able to communicate with TypeDB cluster as well. So what's going to happen is that in this client mediation step, right, for the application to be able to connect to the cluster via the TypeDB client, what's going to happen is that TypeDB client will be fed with the information about the address of the server. Actually, the TypeDB client doesn't need to know about the address of all the servers. It just needs to know one of them. And what's going to happen is when the application requests TypeDB client to connect to the cluster, giving an address of any one of the server, the client will perform this handshake step where it connects to one of the server, and for the server to reply back with the address of the remaining cluster members in the cluster. So in this case, the TypeDB client is supplied the address of server 3 by the application, and server 3 will respond with the address of server 1 and server 2. Now, aimed with this information, it'll allow you to, it'll allow the application to basically perform additional requests, such as performing a database insertion or query to a given database. So when this additional step is taken, right, say the application wants to insert some data into DB1, what's going to happen is that an additional information is exchanged between the server and the client for the server to inform the client that the primary replica of DB1 sits on the first server. And geared with this information, it is possible for the application to make connection correctly to the first server in order for the application to insert the data. Similarly, if the client is then instructed by the application to perform a read any replica, in which it doesn't matter which server the client hits, then the client can just pick any server, and it can do so because it already has information about all the cluster members in the cluster. So the key takeaway from this explanation is the fact that the application can use TypeDB client in a way that is fully transparent. The application doesn't need to know of the fact that there are multiple servers to connect to. It doesn't need to make its own decision for how to connect to each of the server and under which circumstances, because all of these is already being taken care of by the client automatically. So from the user experience perspective, connecting to TypeDB cluster is exactly the same as when you're connecting to a TypeDB instance, in which there's only a single instance. Given that the mediation switching between one server to another is taken care of by the client transparently. Let's make a bigger room for us to be able to take a look at the internals. We're getting deeper here. We're going to take a look at the internals of a replica. Basically answering the question of how do you get your data distributed across all servers? Right. Now that we know that we've got the algorithm for performing client-server communication, now the next step is for us to understand how does the data of a database is replicated between one replica to another. So this is essentially the problem of distributed systems. We want to be able to let these servers, these three servers, to be able to communicate the data from one another in a safe way. There are some assumptions that we can't make in a distributed systems. Like, for example, we all know that machines crashes randomly, and it's possible for for server 3 to crash with server 1 and server 2 still operating. How do we make sure that the data doesn't get corrupted and doesn't get only partially replicated, right? So these are the problems that we're facing here. How do we make data replication work in a safe and also performant way? So we want to start with the right assumptions. There are some base assumptions that we need to make. There are some things that we need to be able to trust, right? So first of all, we need to be able to trust that the CPUs in the servers are not faulty. We want to be able to trust that the CPUs are not lying to us, and we want the CPUs to be able to run the instruction that TypeDB cluster server has correctly. And this is, I think, a safe assumption to make because, like, normally, like we can trust our CPUs and they're quite reliable. The second assumption that I want to make is the fact that disks must be correct. So the disk storage in your computer or in the cloud system, like in your Amazon instance, it needs to be trustworthy and it must not lie to you. And when you say that I want to store this particular bit of data, it needs to be able to store that data reliably and without corrupting it. So these two assumptions are, I think, an easy enough assumption and always holds true in most cases because CPUs made by Intel and disks made by these reputable companies are normally really reliable, right? So therefore, we can safely assume that we can trust these two assumptions. Now, geared with these two assumptions that at least parts of the systems are trustworthy, you can start building a system that tolerates unreliability in some other way. So the unreliability that we're talking here in the case of distributed systems is the fact that, as I said before, server may go down randomly at any given point in time, right? You don't always know that. Networks are also unreliable. Sometimes the connection gets disrupted. Sometimes, data gets sent and is lost. Sometimes data gets sent and usually is duplicated. And sometimes data are basically sent out of order. You send A and then you send B, but the recipient receives B and then A. So these are the things that we cannot assume in a distributed systems. So server may not be always available. Network may not always be available. So we need to build a system revolving around these assumptions and things, and also things that we can't assume, right? We need to build a system that is safe under this condition. And additionally, we also need to build a system that doesn't rely on timing. In a distributed systems, it's really hard to keep clocks in sync between one server to another. Therefore, the algorithm must also assume that timing is something that we can't rely on. Let's make some room in order for us to fit in the internal of what allows TypeDB Cluster to perform replication in a safe way. So we call this component a replicator. The replicator is basically the backbone of TypeDB Cluster's replication and clustering functionality. It allows you to distribute data in a safe way under the assumption that I talked about earlier, about things that it can assume and things that it cannot assume. And therefore, it allows you to replicate the data in a safe and reliable manner, and also in a way that is quite efficient. So this engine allows us to basically run multiple instances of cluster on different servers and be sure that if one of the server goes down or if the network gets disrupted, it won't result in an inconsistent state. We can be sure that the data stays in sync between one another. So the replicator engine is built on top of the RAF algorithm, and RAF algorithm is basically a proven and battle-tested algorithm for building a safe and reliable data replication. So RAF is one of the key components. The other key components that are also quite important is that we've built RAF based on actor model principle, meaning that our RAF implementation is non-blocking, allowing you to leverage maximum performance. It's also built on battle-tested technologies. The storage, we use RocksDB, which is quite battle-tested. For the communication, we use 0MQ, which is also quite efficient, has quite a minimal overhead, and is also battle-tested. So in today's presentation, we're going to take a look at this. I think this is actually the most interesting part of the explanation, which is we're going to take a look at the key ideas of Raft, albeit very briefly, in order to understand how does niche replication work under the hood, right? So Replicator is built on top of Raft algorithm, and the key ideas of Raft is that you keep an activity log in each server, right? And these activity logs rely on the communication protocol such that they are replicated safely and always stays in sync between one replicator to another, between different replicator instances on different servers. So based on this activity logs that is safely replicated, right, it allows the engine to basically reconstruct the state in separate servers, ending up in the same state. Because if you start with the same input and then you apply the same processing, then obviously you will end up with the same output. You will end up with the same outcome. And this is essentially how the Raft works. So you replicate the state machine between one server to another in a safe way. you replicate the activity, and based on this activity, you would reconstruct the state in separate servers in a way that all servers will end up at exactly the same outcome. And these outcomes are basically the state of our database, the TypeDB database. So RAP achieved this despite the fact that network may fail and the fact that the server will also fail, right? By the use of two key steps, which is the step that allows RAF to designate one replicator and exactly one replicator to be the leader replicator. And the other step is for the designated leader replicator to perform the actual replication process between the leader to the other replicator. So in RAF's terminology, we call the other replicator as the follower replicator. And in practice, what that means is the leader replicator will be where we have the primary replica, and the follower replicator is where we'll have the secondary replicas. So let's take a look at the leader election process. So when you start the TypeDB cluster for the first time, say you have 3 servers and you start them at roughly the same time. It doesn't have to be exactly the same because the algorithm is robust for that against that scenario. So you can actually start them, like at slightly different time, and that's going to be completely fine. What's going to happen is if this is the first time you start the server, right? The replicator instance in that particular server will always start as a follower. And in RAF, the election process is identified by a number, just like in the real world, when you're doing an election, you have an election term, right? Like this is election 2021 and this is election 2025 and so on and so forth. In RAF protocol, an election is also identified by an ID, which we call term number. And then in this case, the term number always starts from 0 and they always increase monotonically by 1, such that the first election is going to be designated as election term number 0, and the next one will be election number 1 and 2 and 3 and so on and so forth. Obviously, each replicator holds their own election number, and there is no network synchronization steps that needs to happen. And the algorithm guarantees that even though these numbers are not globally synchronized, the resulting process will end up with an algorithm that is behaving correctly. So here we have 3 servers. All of them are in the state follower, with all of them with the term number 0. And what's going to happen is a follower will propose itself to become the candidate for the leader if the follower doesn't hear from any leader. In this case, because there is no leader, none of the followers will hear from any leader. And when that happens is that these follower eventually will try to attempt to become the leader. So the follower will wait for a specified amount of time, which we call the election timeout. And the election timeout is randomized. In the first server, you see that the election timeout is set at 500 milliseconds. The second server is set at 300 milliseconds, and the third one is set at 700 milliseconds, right? These numbers are randomized in order to minimize the probability for them happening at roughly the same time. So ideally, a good election is where there's only one candidate, because the more candidate you have, the more likely that the votes is going to go is going to be split amongst different servers, in which at the end they can't really decide which one should be the leader, right? So you need to minimize the number of times simultaneous election happens at the same time, and RAF does this by randomizing the election timeout. In this case, the second server, which has an election timeout of 300 milliseconds, is most likely to be the first one to start an election, right? It starts an election by changing its mode from follower to what we call candidate. It also increases the term number from whatever it is plus 1. In this case, it'll start an election at term 1. Now the other two followers, server 1 and server 3, receiving an election request from the second candidate, will reply with a response granting a vote to the replicator on the second server. And when that happens, the second server will not have to wait for every server to reply, but rather it only needs to wait for the majority of servers to grant their vote. And that's interesting because literally what that means is the primary in a cluster of 3 servers will only need 2 votes out of the 3 servers in order for it to become the primary. And given that as a candidate implies that the second server will have already voted for itself, right? So the second server, when it starts an election, it also implies that it has voted for itself, meaning that it only needs 1 more vote from either server 1 or server 3 in order for it to become the leader. So as soon as it receives 1 vote from any of the server, whichever goes first, right, it will elect itself as the leader of term 1 and will start sending a pulse to the other followers continuously. This pulse is important because, as I said before, if a follower doesn't hear from the leader, it will think that the leader has died or just doesn't exist and will start a new election process. And we want to minimize the number of times this election process happens because it will result in performance. It will impact the performance, basically. So when the leader communicates with the follower sending pulses, the follower is then informed of the leader and is informed of the fact that this leader is a leader of term 1. It will also update the number of term. It will also update the term number that it has to the same one as what the leader has. And hence, all the followers will also have the same term number as the leader, which is 1. So the leader election process is based off these simple ideas. I won't really go deep into how they work, but what's important is the fact that this algorithm is actually proven to always work regardless of whether the network gets disconnected or if the packet gets duplicated or is lost or is reordered, and even if any of the instance, including the candidate instance, dies, right? So if, for example, if the instance that becomes a candidate suddenly dies, then what's going to happen is it's going to be fine because eventually the other followers will then be able to start another election. So now that we've understood how this leader election process takes place, and now we have the second server becoming the leader of the cluster, let's make some room and try to understand how the next step, which is the replication step, works. So let's bring up our application back in order to understand how does a replication, how does the replication process happens when an application starts to perform requests to the server, to the cluster, right? So here we have the application and we have the second server hosting the primary replica for the database. What's going to happen is that the application will always communicate with the primary for performing regular data inserts and data reads, right? Let's make some room in order to describe more components in the subsystem. So here we have the replica and we have the activity log. Here I'm depicting the activity log right here, right? And what's going to happen is, say the application wants to insert a new entity with some name, right? A typical insert $P is the person has name Bob. to the server. And this query will have to go through the primary replica, and the primary replica, which is also where the leader replicator for that given database sits, will accept the request, right? Will accept the request and will add that request into the activity log. So that little entry right there with the curly brackets there is essentially the entry. So the insert $p is a person has name Bob is then translated into key values, right, by the storage engine. And then these key values will be appended to the activity log. And now the leader replicator will try to replicate these instances of the key values onto the other followers, right? And this replication process happens indefinitely until all followers receives the entry. So this replication process will happen indefinitely until all of them receive the entry. However, what's interesting is the primary can already respond back to the application saying that the entry has been accepted once, then only the majority of the servers and not all of the servers receives the data. So the primary receives the key value, add that into the activity log, and as soon as either the first server or the third server responds back, it can already immediately respond back to the application saying that the data has been safely accepted. And what that means here is that as long as the data is received by just the majority of the server and not all of the server, we can assume, and the protocol guarantees this, RAF guarantees that the data will eventually be safely replicated across all servers. And this is really cool because what that means is if, let's say you have a big cluster of size 9, right? What that means is the leader only needs to replicate to 5 servers before being able to respond back to the application. And this is a huge performance boost because the amount of time that you can reply back to the server, sorry, to the application is essentially halved, right? You don't need to wait for all 9 servers. You just need to wait for 5 servers. Although, obviously, the replication to the remaining servers are still ongoing and is done in the background, right? At some point, these entries in the activity logs will be replicated to the servers, and at some point they will be committed to the replica. And this is the point where the data is safely stored in the replica. And this operation just keeps on going on. The application does more requests. The primary receives more entries, and this entry gets replicated. And as soon as it gets replicated to the majority, the primary can immediately respond back to the client. And all of these are done obviously in a way that's completely safe because despite the fact that any of these instances may crash, the data will still be guaranteed to not be corrupted. And the transition between one primary to another, should one of the primary crashes, can be done in a safe way. So we've talked about how RAF works. I think it's quite interesting to see that the other challenges is that given the conceptual understanding of RAF, and you're going to be able to implement that in RAF, and obviously when it comes to the implementation, you take the conceptual model and you want to implement them, right? There's an additional challenge there, which is how do you implement RAF efficiently? So RAF is quite a network-heavy protocol. That involves a lot of round trips between machines, one to another, and latency is a big issue, obviously, because waiting for a round trip is easily going to take about like 5 to 10 milliseconds in a data center, even if they're only in a single data center, and like 5 to milliseconds round trip obviously counts and is quite a heavy price to pay. especially given that we have to replicate the data across multiple servers, right? And what we come up with is we need to make sure that the algorithm that we built is implemented in such a way that is concurrency first. So we want the algorithm to be implemented in a non-blocking and in an event-driven way. And we've taken a look at several alternatives. We've taken a look at whether we want to implement that using the brute force thread model or different kinds of other like concurrency means, and we come up with the ideas that an event-driven and non-blocking communication is best expressed as actor model. So here in this diagram, you'll see that we have the leader replicator, which is implemented as actor, and the follower replicator, which is also implemented as actor. And the arrow that you see here on the screen indicates the fact that the leader can keep on sending data to the follower one after another without waiting for the follower to respond. So the leader sends the first request, the blue one, and without waiting for the response for this request, it can immediately send the next one, and the next one, and then the next one. Eventually, when the response is received for the particular request that it did some time ago, then it's going to continue processing this request. But the idea is that after it sends the first one, it can immediately do other things without having to wait. So rather than sending and then doing nothing while waiting for the response, it multitasks, right? It sends the first one, and while waiting for this one, I might as well try to do something else, such as, for example, sending the request to the other followers and to the next follower, or like receiving input from the client, right? It can multitask. So the event-driven and non-blocking communication model has allowed us to make sure that we multitask efficiently, and does so in a reliable way, backed by the actor model library that we've also built. So all of this sounds nice and it's quite cool, but in implementing these, there are a lot of things that we need to take into account, and building a distributed system in a way that's concurrent is inherently quite error-prone, right? So we need to make sure that things that we build, the ideas that we have, can be translated into an implementation that is also not just performant but robust, right? So we've got this idea on how to build this whole thing in a performant and robust way, but how do we actually verify that these things are indeed robust and performant? Well, the answer to that is test, right? We need to test this. And the question comes, which is, how do we build a test that allows us to test these systems in a way that's not also correct, but also allows us to be productive in pinpointing the issues, right? Building distributed systems is inherently non-deterministic, and we don't want to deal in a test environment where the whole thing is flaky and you have to rerun the test 100 times in order for you to reproduce the issue, right? So we want to be a bit more productive than that. And the answer to that is we've come up with the what we call the deterministic simulation, which is a framework which allows us to instantiate the replicator instance, right? We instantiate the replicator instance in the context of this deterministic simulation framework, where we replace the clock, right? The clock is what we use for performing scheduled events, such as performing an election when the timeout has elapsed, or for performing the periodic heartbeat or pulse from the leader to the follower. We do that by using clock, right? So we replace this clock with a deterministic clock. And by deterministic means that things are always scheduled in the exact same order. In addition to the deterministic clock, we also have the deterministic network layer. And similar to the deterministic clock, what that means is that in order for us to simulate network failure, such as packet loss and packet duplication and packet reordering, right? These things can be simulated in a deterministic manner. So the deterministic simulation is really completely deterministic. And given a random number that you input into the deterministic simulation framework, it will allow you to run a simulation of, say, running a replicator for a couple of hours or days in a way that's completely deterministic. So the idea is you just run this framework and you increase the size of the cluster, and you increase the amount of unreliability and randomness in the system, and they're going to perform the events in a completely deterministic way, such that if an issue is reproduced due to some weird interleaving between the messages or the timing for the clock, the next time you run the test, it's going to get completely reproduced. So this is really cool, because what happens is you just keep on running this with different random number input, and as soon as you encounter an issue, you just make sure to keep that random number input in order for you to then reproduce the same scenario. So this framework has allowed us to capture different and weird kind of bug that happens. Like, for example, we have this one issue that only happens in production very, very rarely, and under some failure conditions, depending on the way the leader and the follower transitions from one to another, right? And this issue happened in production, and we can't really troubleshoot why. And at some point, we try to tweak our deterministic simulation, and we come up with a parameter that allows us to reproduce this issue. And from that point, it's just like literally really easy, because you just simply input the same random number that reproduces this issue, and then you can basically allow anyone in the team to take a look at the issue. Hey, here's the test, and here's how you reproduce the test. Here's the parameter of the test, and here's the input, the random number input to the test. And this has allowed us to stay productive, even in the face of working with such a non-deterministic systems that is inherently non-deterministic and quite random, right? So I thought this was quite a cool idea, and we actually didn't come up with the deterministic simulation idea. So basically, one of our team members happened to stumble upon the paper from Apple's Foundation DB, and we were inspired by what they do over there, and we try to learn from them, implementing what they've done in their environment to ours. So I think we've covered quite a lot of aspects of TypeDB Cluster. We've taken a look at what the product has over TypeDB and why you want to use that. We've covered the communication mode of TypeDB Cluster between the client and the server, and the addition mode of the read any replica, which allows you to scale the communication and the number of queries that you can handle in the cluster. Right, we've taken a look at the automated client mediation protocol, which allows you to basically work with cluster from the client in a completely transparent way without any intervention, without having to deal with like selecting the right servers manually. We've taken a deep look at the data replication protocol and the components within the replication protocol, and we've touched about why the replication protocol is quite safe and secure and performant based on the design decisions that we take, which is selecting rough as the backbone of the algorithm, which is an algorithm that is proven to be completely safe to be used in a distributed environment. We've taken a look at how we can leverage actor model to ensure that these the implementations are done in an event-driven and non-blocking way, which allows us to be really efficient, given that there are many waiting between communication between the leader and the follower. And we've also touched base at why correctness is preserved and is guaranteed and is verified carefully with our deterministic simulation testing, making sure that bugs are always easily capturable, and when they're captured, they're always captured. We don't have to run the tests multiple times in order to capture that, once in a 1,000 times scenario, right? So we've talked about the key feature of TypeDB Cluster, which is the scalability and high availability, which is achieved by the replication module and the client mediation protocol. We also would like to say that we've very recently, as of TypeDB Cluster 2.1.0, we've added authentication, which allows you to secure your database from people who doesn't have your credential. We've added encryption, which is, to be exact, it's the in-flight encryption. So we don't yet have at-rest encryption. And what that means is we encrypt the traffic that goes between the client to the server and between the server to other servers, right? They're all fully encrypted. The network are fully encrypted by use of SSL or TLS and the curve MQ algorithm. We don't yet have encryption at rest, meaning that the data that you store in the disk is not yet encrypted, but that will come soon. And there will be more innovations coming your way as well. There will be partitioning and there will be backup, even though that will come at a slightly later time.